we're going to look at strong and weak acids and bases. And we're going to use the lens of conductivity and pH to take a kind of a submicroscopic look at the ions that are involved. We examine the conductivity and pH of acids and bases of equal molarity. That is, we make the acids and bases, in this case, with 0.1 moles of the acid or base in every liter of solutions. We're going to use sodium hydroxide and hydrochloric acid. We're going to use acetic acid, which we'll call H-acetate because each acetate is attached to a hydrogen ion. Formic acid, which likewise is H-formate. Propanoic acid, which we'll call H-propanoate. And butyric acid, which we'll call H-butyrate. And then finally we will use ammonium hydroxide, which is ammonia in water. Here are the conductivities that you find for equimolar concentrations of these things. Here in the 24,000 microsiemens per centimeter, hydrochloric 28,000, and then dropping very rapidly, acetic acid 1585, formic acid 3480, butyric acid 570, and propanoic acid just 390. Then ammonium hydroxide comes in here at 672. Now, we know that strong and weak electrolytes are distinguished from each other by their ionization. Acids and bases are both electrolytes. What that means is that solutions of acids and bases will conduct electricity. Their molecules or fundamental units break up into positive and negative ions, cations and anions. The conductivity that we measure with the conductivity meter measures the concentration of ions in solution. So we might have 0.1 molar of some soluble thing, but it might not be 0.1 molar in ions if it doesn't completely break up into ions. Strong electrolytes will break up 100% into ions. Every one of the molecules ends up as a plus and minus ion. Weak electrolytes will not break up 100%. In fact, most weak electrolytes break up less than 5%. Something like water breaks up way less than 1%. We'll look at a diagram here on the next slide to show what that means. On the left, we see that a strong acid, like hydrochloric or nitric, has broken up into positive ions, hydrogen ions, and a negative ion like nitrate or chloride, bromide, perhaps hydrogen sulfate. And these breakups have been 100%. There's no molecules left in solution. You can't see anything that is still put together. On the other hand, over here, this weak acid, and we've used a 10% dissociation when most acids are way less than 5% dissociated. You can see that nearly all of the HA molecules have stayed HA molecules. Only one has broken up, 1 in 10 has broken up into a positive and negative ion. And we can imagine that this is why the conductivity on the left for the strong acid is much, much higher than the conductivity of the weak acid over here. So let's look at the conductivity and understand that high conductivity means a strong electrolyte. Well, that's obvious. We're up here in the 20,000s. Sodium hydroxide and hydrochloric acid are both strong electrolytes. They have broken up 100% into ions, and so they conduct a huge amount of electricity. Here, the acetic acid, formic acid, butyric acid, and propanoic acid, and the ammonium hydroxide are weak. They have not broken up very much into ions, and correspondingly, we see very low conductivity. Different from each other, of course. The formic acid has a fairly high conductivity, and the propanoic acid has a very low conductivity, but much, much less than what we see in the teens of thousands up here with the very strong acid and base. We then look at the pH, and these are the pHs recorded for these. We notice that a very low pH, like in hydrochloric acid, is associated with a high conductivity. We remind ourselves that the strong acid has broken up 100% into hydrogen ions, and in this case a chloride ion, and therefore the pH is very, very low. We contrast that with the acetic or formic or butyric or propanoic acid, and we see that the conductivities are quite low, and the pHs are higher. And the same thing with the ammonium hydroxide. We see it had a very low conductivity. And now on the base side, this is a base because it's higher than a pH of 7, but it's nowhere near the 12.13 of the 100% dissociated sodium hydroxide.